Welcome to Study Loop.
Hello everyone, today we're doing chapter 14, problem 8, and this question asks us, for the following compounds, label each different type of proton, and then rank the protons in order of increasing chemical shift. Well, let's first go over the chemical shift. So we know if something has a high chemical shift value, it is going to be what we call downfield shifted, and it's going to be on the left of our NMR spectra. And what we know about low chemical shift values is that they're going to be upfield and on the right side of our NMR spectra. So what we know is that around each of these hydrogen nucleus are electrons going around them. And what we know is that these electrons that are localized around the nucleus, they will do what we call shield the proton nucleus from the external magnetic field of the NMR. And essentially what it means is that the force felt from this nucleus by the external magnetic field is actually going to be less than the value of the external magnetic field that's being applied. So you can say that these electrons kind of decrease the effective magnetic field strength observed and felt from these proton nucleuses. So this is what we call shielding. So you can imagine if these protons are next to something electronegative, such as a chlorine or bromine or one of the halides, if they're next to something that's electronegative, this chlorine can pull away the electron density away from this hydrogen nucleus and towards the chlorine nucleus. So what happens to this hydrogen is that now it has less electron density around its nucleus, so it's less shielded. So this means that it's gonna use a higher frequency to cause that spin flip to occur. So it's going to be downfield shifted. So if you look at an NMR spectra, we can think about from the effective magnetic field strength from increasing left to right. So I know the chemical shift goes from 0 and increase right to left, but your field strength will increase left to right. So if you have less shielding from your electrons, then you're going to require a less amount of energy to cause that spin flip. So you're going to be closer to the 0 line on magnetic field strength. And now if I extrapolate this to my NMR graph, it's actually going to be downfield as the larger ppm value on an NMR graph. And if we look at something that's more shielded, for example, this proton here, so this proton is adjacent to one carbon, so it has a whole carbon distance away from these electronegative atoms. So we know that this carbon is going to have more localized electrons around its nucleus, so it's going to require a greater amount of energy to cause that spin flip. So if we know that the magnetic energy strength increases from the origin left to right, we know that if we require more energy to cause that spin flip, that resonance, we know that if we extrapolate this to NMR spectra, we're going to be on the right side of this graph. So we know that we're going to be upfield shifted and more shielded with a lower ppm value or chemical shift value. So I hope that kind of helps us understand. It's kind of confusing because the ppm value, the chemical shift goes right to left, but your field strength increases from the origin left to right, just like a normal graph would. So you can just imagine de-shielding requires less field strength, so it's closer to the origin on the left, or a higher chemical shift value. And if something's more shielded, it requires more energy, so it's going to be more to the right side of the graph with a lower ppm value. So let's first identify the number of unique protons in this question. So what we see is that we have an internal plane of symmetry here, and we have two halides, one of them being bromine, one of them being chlorine, and they're attached to two carbons. So we can say that because of the internal plane of symmetry, we know that these two protons that are directly bounded to the carbon that's bounded to the chlorine will be in a unique chemical environment than these two protons or these two protons. Using the same logic, we can say that these two protons that are bounded to the carbon that's bounded to the bromine will be in a unique chemical environment than these middle protons and the left protons. Using that same logic, we can say that these two protons will exist in its own environment since they're now an entire carbon away, one side being from chlorine, one side being from bromine. And remember, because there's no chiral centers, we don't actually get any different electronic environments on these CH2 carbons here because there's actually no chiral centers. So now we identified we have three unique electrons, or unique protons, sorry, that would generate three unique NMR signals in our NMR spectra. Now let's identify which one would be lowest and which one would be highest chemical shift value. So if we remember, your lowest chemical shift value will be upfield and it's going to be the most shielded. So that's going to be the furthest away from your electronegative atoms. So if we look, this carbon is directly bound to an electronegative atom and two protons. Same with this carbon. This carbon is bound to electronegative atom and two protons. But this carbon is bound to two protons and a carbon and a carbon. So we see that these two protons are furthest away from either electronegative halides on this molecule. So we can say that these red protons will have the smallest chemical shift value out of any. So we can say that they will be the most shielded, so they have the smallest chemical shift value. Now we have two more protons left. We have one being the blue, one being the green protons. So we can say we know that the largest chemical shift value, or the more downfield shifted, is going to be the most deshielded proton. So whichever of these halides is most electronegative, that's going to cause our protons to be most shielded and give us the largest chemical shift value. So we know that chlorine is more electronegative than bromine, because following the trend going right to left, right to up on the periodic table, you know that chlorine is more electronegative than bromine. So chlorine will cause greater deshielding in these two electrons, giving these two electrons a greater chemical shift value because they would be really on the downfield side here on this NMR spectra. So we know that the blue protons would have the largest value because they're bounded to the most electronegative atom, and then that leaves us with the protons bounded to the carbon that's bounded to the next second best electronegative atom, which is the bromine here. So now let's do the same identification on our central molecule here. So we have three protons there, one proton here, one up there, and this is a tert-butyl, so we have 9 protons here. So we have 1, 2, 3, 1, 2, 3, and 1, 2, 3. We'll not draw these out just for the space. But we can imagine, once again, there's an internal plane of symmetry. There's no chiral centers here, so we know that there's not going to be any difference for these CH2 protons like in the previous examples we did. So we know that because this is a sigma bond, it has free rotation and it's achiral internal plane of symmetry, so these 9 protons will all exist in the same chemically unique environment. We also know that these 2 protons in this central carbon is bound to an oxygen, and these will also be in its own unique chemical environment. And that leaves us with this terminal methyl group, which would also be in its unique chemical environment, because this carbon is only bound to 1 oxygen, while this carbon is bound to 2 oxygens. So now we once again have 3 unique chemically distinct protons, and we need to determine from lowest to highest which one is going to be the most shielded, which one's going to be the most deshielded. So let's go with the most shielded. So that's the one with the lowest chemical shift value, and that's the one that's going to be upfield on your NMR spectra. That's to the most right side of your NMR spectra, somewhere over here. So those are the protons that experience the least amount of electron withdrawing from electronegative atoms. So let's investigate. So we see that this carbon here is bounded to an electronegative oxygen atom, so these protons would experience some sort of deshielding. Moreover, this central carbon here is now bounded to 2 electronegative oxygens, so these 2 protons, we can say, would experience even a greater amount of deshielding. But now these 3 protons on these terminal carbons are all bounded to a central carbon here, and then one oxygen. So we have one carbon spacer before we get to the electronegative carbon. So we can assume that because of this distance, these are going to be the most shielded protons here. So they would have the lowest chemical shift value being upfield on our NMR spectra. So we know that these blue protons here will be most shielded. And once again, we know that the least shielded or the most deshielded will be these two green protons, because now these two green protons are directly bounded to two electronegative oxygen atoms. So that would cause the most deshielding. And that leaves us with the red protons being bounded to one electronegative oxygen atom. So that would be middle amount of deshielding. And now if we work on the last problem, we see that once again this terminal carbon here has 3 protons. The CH2 has 2 protons. And its terminal carbon here has 3 protons again. So we know that this CH3 is directly bound to a carbon that's double bonded to an oxygen, so directly bound to a carbonyl group, while this CH3 is just bounded to a CH2. So these two terminal carbons are in unique chemical environments, so the protons they're attached to will also be in unique chemical environments. So these three will be in a unique chemical environment, same with these three. And that leaves us with the middle, 2 protons. Because it's a chiral molecule internal plane of symmetry, these two will be equivalent as well. So once again, we have 3 unique types of protons, and let's see which one will be the most shielded and least shielded. So we know that this carbon is directly bound to one carbon that's double bounded to an electronegative oxygen. So these 3 protons will experience some sort of deshielding. We know that these two protons coming off the central carbon is also bounded to a carbonyl group here, but is also bounded to a CH3 group here. So this CH3 group here, every proton here has some sort of electron cloud around it. Same with the central carbon atom has some electron density around it. So there's a whole cloud of electron density around this methyl group. So we can imagine that there's going to be some sort of inductive donation of electron density towards this terminal group on the right side and also towards the carbonyl group on the left. And then if we look at the right side, we see that these 3 protons are bounded to one carbon here, and then one more carbon away was you have your electronegative carbonyl group here. So we only have one instance of electron inductive withdrawing towards this CH2 bond here for these 3 protons. So because these 3 protons have only one vector of electron withdrawing, while these 2 protons has 2 vectors of electron withdrawing, we know that these green protons will be more shielded than these red protons. But now what about these blue protons? Well, these blue protons are directly adjacent to this carbonyl group, so these have quite a bit of electron withdrawing effect, experience an electron density removal away from these hydrogen nuclei. But once again, this is only one vector, while in the middle we have 2. So we know that the most deshielded proton will be the one with 2 vectors. So that's going to be these 2 red protons. So that's going to be the most deshielded. Well, now what about the most shielded? Well, your most shielded protons will be the ones that furthest away from your electronegative atom. So we see that we're left with the blue proton and left with the green proton. Well, the blue proton is 1 carbon away from this electronegative oxygen, while the green protons are 2 carbons away from the electronegative oxygen. So the green protons are furthest away from your electronegative atom, meaning that's going to be the most shielded. That leaves us with the blue one for the middle in terms of their chemical shift value.